Hey everyone. If you've ever stared up at a towering construction crane, peeked inside a delicate grandfather clock, or even just looked down at the gears on your bicycle and thought, how on earth does that actually work? Well, you are in exactly the right place. In today's explainer, we're going on a builder's journey. We are going to strip mechanical engineering right down to its elegant, basic foundations so you can see the hidden mechanics powering the world around you.
All right, here's our 5-step blueprint for today. We'll be hitting the physics of movement, the inventor's toolkit, the efficiency problem, designing compound machines, and finally, test, refine, and perfect. Let's get right into it.
This 5-day masterclass blueprint brilliantly lays out our exact flight path. It's taking a pretty rigorous academic concept and turning it into this empowering journey of invention. It flows so logically, right? We start on day 1 with the absolute foundations of motion, crack open simple machines on day 2, and then hit the math of energy loss on day 3. Then, days 4 and 5 are all about shifting from pure theory into actual practice, getting your hands dirty designing, building, and refining real prototypes.
Step 1. The physics of movement. The invisible forces driving our world.
Now, it is honestly fascinating when you realize that all of the insanely complex movement around us really just boils down to 2 super simple types. Seriously, strip away the noisy engines and the shiny metal casings, and you're left with this. Translational motion, which is just linear movement straight from point A to point B, kind of like pulling out a sliding drawer, and rotational motion, movement spinning around a fixed pivot, like a turning gear. Figuring out whether a specific part slides or pivots, that is the absolutely crucial first step to thinking like an engineer.
And that leads us straight to our golden rule. Machines are simply systems designed to manipulate motion to perform work. That's it. No matter how incredibly complicated a mechanism might look at first glance, its one and only job is just to manipulate those 2 basic sliding or pivoting motions to get work done. Once you embrace that concept, the entire mechanical world suddenly feels a whole lot more approachable.
Step 2. The inventor's toolkit. Let's look at simple machine mechanics. Okay, let's open up the toolkit. Here we have your 6 classical simple machines: the lever, the wheel and axle, the pulley, the inclined plane, the wedge, and the screw. These are the literal, fundamental building blocks of all mechanical engineering. I mean, every skyscraper crane, every sports car engine, they're all just brilliant, fancy combinations of these exact 6 things. Dissecting them reveals how they fundamentally alter the laws of physics to work in our favor. So how do they do it? Well, it's all about managing force. Whenever we analyze a machine, we're really just tracking 2 specific things. First is the input force. That's where your effort actually enters the system. Second is the output force, where that force exits the system to do the actual heavy lifting. By tracking this exchange, it becomes clear that simple machines exist purely to change the magnitude, like the raw strength, or the direction of that input force.
Moving to step 3. The efficiency problem. We're getting into the mathematics of mechanical advantage.
Now we are hitting the core reason we even bother using machines in the first place, and that is mechanical advantage. It's actually a super simple calculation. You just divide your output force by your input force, and that ratio tells us exactly how helpful a given tool is. If you put in a tiny little bit of effort, but you get a massive output force on the other side, boom, you've got a high mechanical advantage. The machine has literally multiplied your effort. Which leads us to a fundamental, and honestly, a wildly frustrating truth of physics. If the math tells us we can multiply our effort, why on earth is no machine 100% efficient? Why can't we ever get out exactly the equivalent to what we put in? It's a harsh reality that every single designer and engineer has to face eventually.
The culprit? Friction. You see, efficiency is really just a measure of how much useful energy actually survives the process. And unfortunately, a portion of your hard-earned input energy is always going to bleed out as heat because parts are rubbing together. So an efficient machine is simply one that minimizes that inevitable loss, trying to keep the output as close as humanly possible to the input.
All right, step 4, designing compound machines. Time for synthesis and prototyping.
So what do you do when one simple machine just doesn't cut it? You build a compound machine. That's just 2 or more simple machines working together. This is where the real magic of synthesis happens. They let us perform unbelievably complex tasks just by breaking those tasks down into simpler, sequential motions working in tandem. You hook a rotational motion over here to a translational motion over there, and suddenly you've got a system capable of doing entirely new work.
Let's see how this actually plays out in a prototype workshop. Imagine this design challenge. Your goal is to lift a heavy weight to a specific height,
But here's your constraint. You have to use the least amount of input force possible, meaning you've got to maximize that mechanical advantage we just talked about. And the requirement? You must combine at least two simple machines. So you might sketch a blueprint combining a pulley to change the direction of your pull and a lever to amplify your strength. It really forces you to integrate everything we've covered into one cohesive design.
Finally, step 5. Test, refine, and perfect. Let's evaluate real-world efficiency. This iterative loop is absolutely crucial for any creator because the real world is messy. Step 1. You build the physical prototype. Step 2. You test it. Does it actually lift the weight easily? Step 3 is where you get hypercritical. You look for energy-draining bottlenecks. Physical testing is going to expose things like sticky pivot points where friction is just stealing your energy. And then, step 4, you figure out why it's happening and you refine the design, over and over until it works.
Okay, before we wrap up this explainer, let's quickly lock in the 3 critical takeaways you need for your own design thinking. First, efficiency simply means your work output closely matches your work input. Second, you have to account for friction. Always carefully watch the pivot points of your rotational components because that is where you lose your power. And third, synthesis. Never forget that the most complex mechanical tasks in the world are really just simple, sequential motions linked together.
So, I want to leave you with a final thought to chew on. Knowing what you know now about sliding and pivoting, about input forces, and that pesky reality of friction, what invisible mechanical advantages are hiding in the everyday objects around you right now? Seriously, take a second, look around the room you're in, and try to deconstruct the hidden physics powering your day. The world is built on these principles, and now you've got the blueprint to see them. Thanks for hanging out with me on this explainer. Keep observing and keep learning.